The next topic we're going to deal with is what we call average acceleration. This builds on the previous two topics that we kind of talked about before. The first one being displacement, which we said was delta S, which was basically our change in position. And we said, well, if we know how much time that position change took, we could figure out what we call our average velocity, which is how much our position changed in a certain time interval, the rate of change of position. And you might have remembered, this would be, if we'd use SI units, would be usually measured in meters, very similar to a distance. This should be measured in something called meters per second, which is, again, saying in this, how many seconds, let's just say we had a speed of 5 meters per second. That means in 1 second, we now have gone 5 meters. In 2 seconds, we now have gone 10 meters. In 3 seconds, we now have gone 15 meters, and so on. And that's a relatively easy thing to kind of recognize, because 5 meters per second just indicates for every second we're traveling, we're going to be going 5 meters ahead of our starting position. Well, we can incorporate one other rate into this, and this is basically the average acceleration. And if we continue to do what we did before, where we basically said, for average velocity, let's just go back a little bit, we said delta S over the time. Well, for average acceleration, we're going to do the same thing. We're going to take our delta V, our change in our velocity, and divide that by the time. Which, if we look at this from a unit standpoint, it's going to be in meters per second per second. What does that tell us? That for every second, again, if you start with this bottom second, our speed will change by so many meters per second. And well, I think a good way to do this is kind of work through an example and talk through some of those things. I guess if you wanted to give us an average acceleration definition, it would be the rate of change of velocity. And this is also a vector, meaning we need to give it some type of direction so we understand what's going on. Sometimes the direction is just as simple as positive and negative. Sometimes we might say east, west, north, south, or give it some type of degree. But average acceleration is basically just continuing this rate of change kind of sequence, where we started off with changing our displacement to figure out our change of position. If we know the time it took, we could figure out the rate of change of that position, which we called velocity or speed. And if we know the rate of change, or if we know the time interval that change took place in, we could figure out the rate of change of the speed, which again is our acceleration. So we're going to go down to a very simple example here. And it says Sally drove from rest to 12 meters per second in 10 seconds. Then she slowed her car down to stop in 4 seconds. So I'm going to give Sally a real simple car here. And she starts off from rest, so our velocity at this point is equal to 0. She then increases her speed. The time it takes that to happen is 10 seconds. And at this point, her velocity now is equal to 12 meters per second. And then in 4 seconds, her speed now goes back to 0 meters per second. So there's really two different intervals we are going to look at. The starting speeding up interval and then our last slowing down interval. And we want to know what our acceleration is. So acceleration, based on our little formula from this before, is delta V over the time it took for that to happen. This will be V2 minus V1 divided by, let's make this delta time, T2 minus T1. A lot of times, again, this T will be just the total time, but we should be careful we're not just slopping that in there. This is really a change in time interval. So you need to know the final and starting times. Her speed here was 12 meters per second at the end of this 10-second interval, and it started off as 0 meters per second, and then the time it took for that to happen was 10 seconds, and it started from 0 seconds, which means our acceleration in this case is going to equal 1.2 meters per second, also called 1.2 meters per second squared. Now, what does that mean? For every second that Sally was driving, her speed gradually increased. So she might have been going 0 here, somewhere here she might have been going 1.2, then she'd be going 2.4, and then maybe a farther down, I'm not going to write the numbers, it's getting really crowded, but you just add another 1.2 on there, so 3.6, and gradually her speed will increase every second she's going until she gets to 12 meters per second. At this point, she actually stops speeding up and starts to slow down and goes the other direction. So let's figure out the acceleration for that. So average acceleration is going to equal, again, v2 minus v1 all over t2 minus t1. This time she ends up going 0 meters per second, but she started off going 12 meters per second. So it looks similar to other equation, but this time the opposite order. That is significant because it makes it negative. So negative accelerations basically mean that we're going to have our speed change differently than what it did for the first part. T2 minus T1. Now, we could put 14 seconds in here. I guess this would be like our 14-second time interval, and this would be our 10-second. Or we can know that it's happened over 4 seconds. But because we're starting out, we might not be real sure about this. Let's go 14 minus 10 seconds, which when I figured this out, her speed now is going to be 12 divided by 4, negative 12. Let me rewrite that. I was going to press it up. Negative 12 divided by 4, which is going to be negative 3 meters per second, which means for every second that she was going on this path, she was losing 3 meters per second of her velocity, which means she was slowing down. So the important thing to kind of notice here, when you have a positive velocity, a positive acceleration will make your speed increase. When you have a negative acceleration and a positive velocity, now your speed will start to decrease. So there's really a couple different things going on there. Hopefully this gives you a good idea of what average acceleration is, how it's calculated, and kind of what happens when you have a positive acceleration and a negative acceleration. So what I'm going to do is I'm going to add one more slide, and that's when I want to talk to you through a few scenarios. So I'm going to insert a page here real quickly, and we'll just kind of leave this white to kind of continue with our same stuff. Here's what I want you to think about. If I have a positive velocity and a negative acceleration, the two signs kind of work against each other. So what we're going to say is our velocity will decrease. We're going to slow down essentially. If I have a positive velocity and a positive acceleration, my velocity, I'm just going to put v, will increase. Again, when you have the signs that are the same, both positive, it's going to increase. Signs that are the opposite, you will have a decreasing velocity. If I have a positive velocity and 0 acceleration, then my velocity will not change. Okay. Just kind of changing up this. If I have a negative velocity and a negative acceleration, I'm going to make these into arrows. My velocity increases in the negative direction. And I guess this is probably one of the main reasons we're kind of going through this last little notes on this little video, because negative accelerations do not always make something slow down. they could make something speed up depending on what your velocity is to start with. If you have a negative velocity and a positive acceleration, it's going to do just the opposite. Your v will decrease. Oops, that's supposed to be r. Let me just take that out of here. Your velocity will decrease. And if I have a negative velocity and if the acceleration is equal to 0, well, my v does not change. So let's just take a real simple look at throwing a ball into the air. And what I'm going to do is select everything and take this out of here, talk you through one final example, and say, okay, if I just take a ball, I throw it up in the air, let's say I throw it really hard, I give it 15 meters per second of velocity. And this ball is going to travel up. But we know that there's something that's going to make this slow down. We don't throw balls up in the air. They don't go up forever. We know gravity works against us. Eventually we're going to get to a point where that acceleration, and that, I guess if we make this positive, then our acceleration would be negative. And that's all we're going to worry about now. We're not going to worry about what gravity is at this point. But that's going to make us eventually get to a point where our ball will stop. But we then know that this ball is going to come back down. And now we're going to have a negative acceleration kind of working on that here. And eventually this ball will start to fall back down and have a negative velocity. So I guess what we wanted to show you here was when you have velocities that are moving against accelerations, if the acceleration doesn't go away, this will then make this continue to go the other direction and fall downward. So that's just a real brief explanation on acceleration and where it comes from.